Despite covering more than 70% of the Earth's surface, the ocean, particularly its deepest parts, remains largely uncharted. While we have mapped the surface of Mars in astonishing detail, vast portions of our own seabed remain unseen by human eyes. The deep ocean is a realm of extremes, profound pressure, near freezing temperatures, and perpetual darkness. Yet it teems with life, geological activity, and complex ecosystems. Recent technological advancements have allowed scientists to probe these mysterious depths, revealing a world that challenges our understanding of biology, geology, and even planetary science. This article explores the characteristics, life forms, geological structures, and ongoing human efforts to understand and protect the deep ocean. The deep ocean is commonly defined as beginning at depths greater than 200 meters, where sunlight no longer penetrates sufficiently to support photosynthesis. This region includes the mesopelagic zone, 200–1,000 meters, the bathypelagic zone, 1,000–4,000 meters, the abyssopelagic zone, 4,000–6,000 meters, and the hadal-pelagic zone, deeper than 6,000 meters. Conditions in these zones are extraordinarily harsh. Pressures can exceed 100 atmospheres, roughly equivalent to the weight of 50 jumbo jets resting on a single human body. Temperatures hover just above freezing, typically ranging from 5 degrees Celsius to 4 degrees Celsius. Moreover, the absence of sunlight means that primary production, the basis of most ecosystems, relies on alternative energy sources, such as the chemical-rich emissions from hydrothermal vents. In addition to extreme physical conditions, the chemical environment is also distinctive. Oxygen levels are variable, and certain regions, known as oxygen minimum zones, can be almost devoid of this essential gas. Despite these challenges, the deep ocean supports a surprising diversity of life. The organisms that inhabit the deep ocean have developed remarkable adaptations to survive under immense pressure, scarcity of food, and complete darkness. One of the most extraordinary features of deep-sea organisms is bioluminescence, the ability to produce and emit light through chemical reactions within their bodies. Creatures such as lanternfish, vampire squids, and certain species of jellyfish use bioluminescence to attract mates, lure prey, or confuse predators. In some cases, intricate displays of light are used for communication in an environment where traditional sensory inputs, like sight and sound, are limited. Physical adaptations are equally fascinating. Many deep-sea fish have gelatinous bodies that resist the crushing pressure by minimizing rigid structures. Others, like the anglerfish, have evolved to possess large extendable jaws and expandable stomachs, allowing them to consume prey larger than themselves. Certain species have developed extraordinary sensory organs to detect minute vibrations or chemical signals in the water. Since food is scarce in the deep ocean, many organisms exhibit opportunistic feeding behaviors. Some are scavengers, relying on marine snow, a continuous shower of organic debris falling from upper layers of the ocean. Others are predators, while certain species, such as tube worms near hydrothermal vents, engage in chemosynthesis, using chemical reactions rather than sunlight to create energy. The deep ocean is not a featureless expanse. It is sculpted by an array of dramatic geological formations, many of which rival the grandeur of terrestrial landscapes. Mid-ocean ridges, such as the Mid-Atlantic Ridge, are underwater mountain chains formed by tectonic activity. Along these ridges, hydrothermal vents spew mineral-rich fluids into the ocean. These vents support unique ecosystems based entirely on chemical energy rather than solar energy, and host organisms that exist nowhere else on Earth. Deep-sea trenches, like the Mariana Trench, the deepest known point in the world's oceans, are formed by the subduction of one tectonic plate beneath another. These trenches reach depths greater than 11,000 meters and are characterized by extreme isolation and extreme pressure. In contrast, abyssal plains are vast flat regions covered with fine sediment. Although they may appear barren, they support a range of life forms adapted to the stable yet nutrient-poor environment. Seamounts are underwater mountains that rise from the ocean floor but do not reach the surface. They act as oases of biodiversity, interrupting ocean currents and providing habitats for a variety of marine life. Cold seeps, where hydrocarbon-rich fluids leak from the ocean floor, also create specialized ecosystems sustained by chemosynthetic bacteria. Exploring the deep ocean presents unique technological and logistical challenges. Early attempts to understand the ocean depths were limited to primitive-sounding lines and dredging. However, the 20th and 21st centuries have witnessed remarkable advances. The development of manned submersibles, such as Alvin and Deep Sea Challenger, enabled direct human observation of the deep ocean. Remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, have since revolutionized exploration by allowing scientists to gather data from otherwise inaccessible locations. These vehicles are equipped with high-definition cameras, manipulator arms, and a variety of sensors capable of measuring temperature, salinity, and chemical compositions. Historic expeditions, such as the HMS Challenger Expedition, 1872 to 1876, laid the foundations of oceanography. More recently, missions like the Five Deeps Expedition have systematically explored the deepest points of all 5 oceans, contributing greatly to our understanding of these hidden realms. Despite these advancements, exploration remains difficult. Equipment must withstand extreme pressure and corrosive conditions, and deep-sea missions are expensive and time-consuming. Communication between deep-sea vehicles and the surface is also challenging due to the limitations of acoustic signaling underwater. The deep ocean plays a crucial but often overlooked role in regulating the Earth's climate. One of the most vital processes occurring in the deep ocean is carbon sequestration. Phytoplankton in surface waters absorb carbon dioxide during photosynthesis. When these organisms die, they sink, effectively transporting carbon from the atmosphere to the ocean floor, where it can be stored for centuries or even millennia. Deep ocean currents, part of the global thermohaline circulation, are responsible for distributing heat around the planet. These currents help moderate climate by moving warm water from the equator toward the poles and bringing cold water back toward the equator. Disruptions to these currents, whether through global warming or other factors, could have profound effects on weather patterns, sea levels, and marine ecosystems. Climate change is also causing ocean acidification, as increased atmospheric carbon dioxide dissolves into seawater, lowering its pH. This has detrimental effects on marine life, particularly organisms with calcium carbonate shells. Additionally, warming waters are leading to deoxygenation, further stressing deep-sea ecosystems. As technological capabilities improve, the potential for deep-sea exploration and exploitation grows. Interest in deep-sea mining for minerals such as cobalt, manganese, and rare earth elements is increasing. These resources are critical for electronics, renewable energy technologies, and other industries. However, deep-sea mining poses significant ecological risks, including habitat destruction and sediment plumes that can affect vast areas. The unique adaptations of deep-sea organisms offer promising avenues for biotechnology and medicine. Compounds isolated from deep-sea microbes have shown potential as antibiotics, anti-cancer agents, and enzymes for industrial use. Given the fragile nature of deep-sea ecosystems, many scientists and conservationists argue for stronger protections. International frameworks, such as the United Nations Convention on the Law of the Sea, UNCLOS, play a critical role in governing activities in international waters. However, enforcement remains challenging. Developing ethical guidelines for exploration and exploitation is crucial to ensuring that the deep ocean's treasures are not destroyed before they are even fully understood. The deep ocean remains one of Earth's final frontiers. It is a place of mystery, wonder, and profound importance to the planet's health and future. Continued exploration, conducted responsibly and ethically, will not only expand our scientific knowledge, but may also provide critical resources and insights necessary for humanity's survival. Balancing curiosity, economic interests, and environmental stewardship will be key to unlocking the secrets of the deep ocean without compromising its delicate ecosystems.